All right, here we go, 2015, starring Michael McCune. So we get into the last two chapters, chapter 11 and 12, and this is kind of what people usually think when they think geometry. Length, area, volume. We've avoided it for the most part throughout the course of the year, doing all the triangle work and circles and proofs and theorems, and now we get to, like I said, what people traditionally think of as geometry, which is length, area, volume. Today we're going to focus on triangles and parallelograms. Two quick vocab words. You've got bases of a parallelogram. Well, what is a parallelogram? Quick review. You should know. Steve?
It's a quadrilateral with 2 sets of parallel sides.
Quadrilateral, 4 sides, 2 sets of parallel sides. So we've got a set of parallel sides here and a set here. Opposite angles are always what?
Congruent.
Congruent. Opposite sides are always congruent. Okay, very good. Now the bases of a parallelogram, there's 2 sets of bases in a parallelogram. It really depends on which one you're looking at. You can pick either set of opposite sides. So some people might call the green shaded the bases of this parallelogram. That would be fine. Other people might call the red shades the base of the parallelogram. It doesn't really matter which side you call the bases. But the height of a parallelogram is determined by which side you pick as the bases. So the height is going to be the distance between the bases. If I pick the green sides to be the bases, well then my height would be that distance between them. What if I pick the red though? How would I find that distance? Addison?
How would you find it?
Yeah. Hayden?
You have to find the length of the segment that is perpendicular to one of the bases and one set to the other base.
Yeah, so if I took this same thing, I'm going to try to recreate it here. Okay, if I took that, it's almost like if you were to take it and turn it. Oh. Why did I lose a piece? I suppose I need to do all 4 pieces together. 1, 2, 3. If I took it and I turned it like that, sometimes it's easier for people to visualize. And then like Hayden said, if you drop this perpendicular from here down to here, that would be the distance between their bases. So again, it really doesn't matter which side you pick. There's a whole bunch of postulates that go in here. Remember, postulates we don't have to prove, which should be a little small celebration in your world, right? Area of a square postulate. The area of a square is the square of the length of its sides. Of course, you just take length times width. What's up, Mr. Natchez? A theorem sheet. You should stand right in front of the board and wave. You should do it. All right, theorem sheet, there you go. You should wave. Had his chances, 5 minutes of fame. Of course, how do you find the area of a rectangle? And yes, that is a rectangle. How do you find the area of a rectangle? Benj?
Length times width.
Length times width, and of course if it's a square, the length and the width are the same, so length times length, we just length squared. So we get the square of the length of the side. Postulate 25, the area congruence postulate, which I don't really agree with. It says if 2 polygons are congruent, then they have the same area. I suppose it could be area congruence. Doesn't necessarily mean figure congruence, because I could make a triangle, might have the same area as that square. Are the figures congruent? No, but are their areas congruent? Sure, they could be. Oliver?
It's not a biconditional statement.
It's not a biconditional. What's that?
It works one way.
Well, biconditional statements, they only go with theorems, if and only if. Congruence postulates,
Saying
what's that?
they're congruent, then they have the same area.
Yeah.
Not saying that they have the same area.
Okay, I see what you're saying. If 2 polygons are congruent and they have the same, okay, yeah, it's not an if and only if. Postulate 26, area addition postulate, just says we can break a figure into different chunks, add up the areas, and we'll have the total area. The area of a region is the sum of the area of its non-overlapping parts. You can break it up into pieces, add them up, or take the sum, and you'll be good to go. A couple others. Area of a rectangle we already talked about, product of the length and the width. Anybody know how to find the area of a parallelogram? Addison, do you know?
Multiply the base by, or multiply one of the bases by the height, which would be the distance between that base and its opposite.
Yep, so base times height. Kind of same as a rectangle almost, length times width, except in a parallelogram we call it base times height. Area of a parallelogram is the product of a base and its corresponding height. Area of a triangle, you guys have dealt with that one quite a bit growing up. What is it, Hayden?
It's half the product of its base.
Half the product of a base and its corresponding height. Now, notice theorem 11.3, you can prove a theorem. Anybody think they could tell me why? If I called this the length and this the width, anybody think they could tell me why that the area of a triangle is length times width? This isn't necessarily a right triangle, but we can. Hager, what do you think?
Because if like you do the width times the length, it would be like two of the triangles making a rectangle, and then so half of it would be the one triangle.
Yeah, so if you extended those out, the area of that rectangle would be length times width. That's given from a postulate, which we don't have to prove, but we've only have half of that rectangle with our triangle, so yeah, it's a quick, nice little proof. Example 1, find the area of a parallelogram ABCD. Okay, parallelogram, base times height. It really depends on what you pick for your base lengths. You don't have that?
Wait, I think it might. It's all messed up.
The copy gods.
We don't even like have like.
Let me see your second. Is it
Like how it says 11.1, we don't have any of the other ones. We have the entire typos for 11.1.
I know.
All right, well, we'll figure it out.
3, 2, 4, 2.
Use AD as the base. If we call AD the base, the other base would be BC. Now, if you're going to use AD as the base, you need to find the height between the bases, which would be drop a perpendicular. They don't show it in the figure until way over here, is if you extended this base out, and then they tell us the height's 4. So the base is extended to measure the height, CF. So the base we've got is what? If we're using AD as the base is 9. The height is, I'm just plugging and chugging, 9 times 4, 36 square units. Now if somebody else came along and used this base right here and this base without measuring, could somebody tell me what the distance is from this base to this base? Logan?
4.5.
4.5. How'd you get that?
Because their segment BD is like a height
Yeah.
for AB and CD.
Yeah, they showed it right here, right? It's harder to visualize when it's drawn diagonal. But again, if I took it, let me see if I can go like this. If I took that figure and I turned it, they gave us that distance right there. It's 4.5. So if we chose the height as BD, we'd have the base of 8, and the height was 4.5, and if you take base times height, 8 times 4.5, look at that, you get the same exact thing. So it truly doesn't matter which one you call the base. As long as you use the corresponding height, you're good to go. Okay. Who could do number 2 really quick for me? Steve? 119, base times height. Base, 17, height, 7. 10 times 7, 70. 7 times 7 is 49. Add them up, we're at 119 what? If we're not labeled, we're going to call it square units. All right, how about number 1 here? We haven't talked about a triangle, but we could just quick use the theorem. What would we have to substitute into the formula if we're going to find the area of that triangle? Hayden?
1/2 66 times 28.
1/2 times 66 times 28. Where'd you get 66 from?
I was going to do that together. But
Yeah, the entire base, you have to add up. 45 and 21 gives us 66. Some people say 1/2 times the height times the base, or 1/2 times the base times the height. Other people like to say base times height divided by 2. It's the exact same thing. Dividing by 2 is the same as multiplying by 1/2. What's that going to be? 33 times 28?
24.
What is it?
924.
924 square units. Okay. Jump to example 2. It says the base of a triangle is 4 times its height. So this time we have some unknowns. We're involved in algebra. The area of the triangle is 50 square inches though. Find the base and the height. So we assign variables. If we call the height h, we know the base is 4 times that, so 4h. Well, we know the area, they told us that's 50. So if we substitute into the formula, 1/2 times the base, well, we know the base, we're calling that 4h. How can we get rid of that 1/2 really quick?
Then with 4H, you just get 2H.
Okay, yeah, half of, well, you know, if we simplify this, 4h times an h is 4h squared. What happens when you take half of 4h squareds?
2h.
You have 2h squareds equals 50. Now you could just divide by 2 and you've got h squared equals 25. Now there's 2 solutions, only one makes sense though. What are the 2 solutions to that equation?
Plus or minus 5.
Plus or minus 5, because -5 times -5 is also 25, but can't have a negative distance, so in this case h equals 5. The height is 5 inches, which means the base is 4 times 5, or 20 inches. Now notice the little note in the side here. If you're not given a nice triangle like we were given, sometimes you just have to drop that perpendicular down. Whatever you call the base, you might have to extend the side length and then drop a perpendicular down to find that height. Algebra, parallelogram has an area of 133. Look at that nice Zeidler, look at that thing. 133 square feet. Height is 19. How could I figure out the base? Just set up the equation for me. We don't need to actually solve it. Benj?
133 divided by 19.
Yeah, 19 times the base, height times base. So yeah, 133 divided by 19. Okay, example 3. Finish up with this one. A robotic vacuum cleaner can clean 2 square meters of carpet in 8 minutes. How long is it going to take for it to clean the carpet hovering a room with the dimensions shown at the right? First, let's think unit rate. How fast does this thing clean? How many meters per minute? How many square meters per minute?
A quarter,
A quarter. Well, how'd you get that?
because 2 divided by 8 is 4.
Yeah, if you take 2 square meters in 8 minutes, if you just find the unit rate and divide, you got 0.25 square meters in 1 minute. And we might use that later, we might not, I don't know. It's just good to review how to find a unit rate. Oops. Let's get that out of the way. Now, earlier we had a postulate that said you can break things up, correct? So let's break this thing up. How could you break it up, or what would make sense? Probably 2 different ways to break it up. What do you think, Tony?
Draw a line that separates, like a horizontal,
You want to go there?
yeah.
Okay, so if we split this figure up into a rectangle and a square, how are you going to find the area of the rectangle? Anna?
Well, if you like extend to the side of the 5 so that you know like the other side where like the dashes for the rectangle is 4.
Okay, yeah, if this whole thing here is 9. Hi, Mrs. Lemley.
Do you need the old test?
Yes, please. Thank you. So yeah, if the whole thing's 9 and Anna's saying if this is 5, that leaves 4 for here, right, Anna? So how would you find the area of the rectangle?
Just 1 times 7.
And then the square is 5 by 5. So if we just add up the areas, we've got 36 and 25, 61 square meters. Now we could use dimensional analysis to quick figure out how long it's going to take. One way you could figure out is we know it takes a quarter or a minute to do 0.25 square meters. So how could I figure out if I have 61?
61 by 0.25 meters.
Careful. Milton?
Multiply 61 by 4.
Multiply, yeah. See, we only get a quarter of a square meter in a minute. So in 4 minutes, we'd have 1 square meter. Every square meter takes 4 minutes. So we'd have to take 61 times 4. Now, we could use dimensional analysis. We wouldn't even have to worry about that 0.25. Sometimes people get screwed up with the decimals. We know we've got an area of 61 square meters. We could multiply by a conversion factor that we have. We know it takes, what was it, 2 minutes per, was it 8 square meters?
2 square meters.
Oh, I'm sorry, other way around. 8 minutes. Nice 8 for 2 square meters. Now the question is, why did they set it up like this? Why did they put the 8 on top and the 2 on bottom instead of the 2 and the 8? Why did they set it up that way?
Because then it equals 4.
Because then it equals 4. Okay, if you simplified it, it'd be 4 minutes per square meter. Yeah? Why else? Quick?
Meter labels.
Yeah, remember labels, they only cancel out if they're literally on top and bottom. So when you use dimensional analysis, and I like looking at this because when you guys do your honors chemistry classes at South, you're going to have to use dimensional analysis all the time. And to cancel out labels, if you're ultimately trying to get minutes, you have to cancel out square meters, which means if you've got 1 on top and 1 on bottom, they're going to cancel. Now you just do the dance with the numbers. 61 divide by 1 times 8 divide by 2, which is like 61 times 4, what do you get? 244 minutes. So it takes 244 minutes, or about 4 hours. Now, it seems like a lot of effort for a robot when, Chris, you could probably do that thing in like 30 seconds, as athletic as you are, right?
Oh, yeah. Those golfing muscles.
All right, I think we're good for the day.